Hi there, my name is Matthew Nichols, a materials and applications engineer here at Brighton Science. Brighton Science is a paramount expert in surface intelligence and quality control. Quality control is central towards achieving a successful bond process. This is relevant to almost every industry on the planet, from aerospace to automotive to biomedical to food packaging, needs to maintain a high standard of quality in all of their processes. One of the central aspects of maintaining a high standard of quality is intelligence and knowing the state of a surface. The tool that we'll be demonstrating today that quickly and reliably gauges the state of a surface is the BConnect. We already have an experiment outlined for us on the BConnect, so it's just a matter of selecting it and starting it. So now we're going to take our baseline as received measurements. 87, 90, 87. So we're consistently in the high 80s to low 90s range for our contact angles. Generally, a clean piece of aluminum would yield expectantly around 50 or below of contact angle values. The fact that we are around 90 degrees tells us that we've got a very low energy surface, which is likely indicative of surface contaminants. In order to remediate these surface contaminants, we're going to clean the surface with a simple isopropyl alcohol wipe. I'm going to start by applying my alcohol to the wiper and do 4 unidirectional wipes across the surface of the aluminum coupon. I'm taking care not to reuse the same surface of the wiper twice and to not trace my path with that same wiper. I then follow it up with a dry wipe to remove any partially dissolved contaminants in the remaining solvent. Now, let's see how our contact angle changed with a simple solvent wipe. "76, 76, 70. So, as you can see, with a simple alcohol wipe, we've reduced the contact angle by about 10 degrees, which tells us that we've improved the state of that surface. Now, we are still in the mid-70s, which means that we could do a lot better. So we're going to follow this next up with a manual surface abrasion. Here I have 180 grit aluminum oxide sandpaper that I'm going to apply to 1/2 of this coupon. What we're doing here is abrading away low energy oxide groups that are building up on the surface to get at the higher energy bare metal underneath. And we remove the debris with a simple dry wipe. Please note that the dry wipe is just an optional step. Now that we've abraded our surface, let's take a look at the contact angle via BConnect to see how that surface has changed. "24, 28, 24. And just in the course of about 30 seconds, we've gone from a 76 to a 24-degree contact angle, reducing it by about 50 degrees. That is indicative of a significant change in the surface energy and the bondability of that aluminum surface. So, we know what the surface analyst does when everything is going well in our process, as we're generating the data that we would expect, but what happens when something goes wrong? Take, for instance, this sandpaper, which is similar to this type of sandpaper, 180 grit aluminum oxide. We've got our same clean aluminum surface, same operator, different type of sandpaper, but in theory it's the same. So, same operator, same type of sandpaper, Same surface, we should get the same results, right? $79, $77, $76. So what happened? I thought everything was the same. Why are we getting a 50-degree difference in our contact angles? And the answer lies in the type of paper that we used. This gray paper is clean. This purple paper uses a compound known as a stearate. Stearates are essentially a detergent that are used as an anti-clogging agent, which is great if you want to prevent the buildup of sanding debris, but pretty bad if you don't want something to transfer onto that surface, as evidenced by a 50-degree difference in our contact angle. This highlights exactly why quality control is so vital to every process, because a change as simple as a different brand of sandpaper could make or break a bond.